Let me thank you and Alan for inviting me here. It's so wonderful to get away from the administrivia of home, and indeed the only improvement I could suggest in these halcyon surroundings is if you could somehow disable the email connection between Australia and Cambridge. It would be absolutely perfect. Anyway, I'd like to talk about some work which is not new work but continues to be useful, and I thought might be of interest in the light of the this 6-month program. And it is a more sort of general question. I mean, as most of you know, my principal work has been in seeing what we can do numerically, developing smarter algorithms for extending series, and then seeing what we can determine from these series. Now, traditionally, that sort of information has been about the asymptotics, and has allowed us to conjecture things like critical exponents, either exact rational exponents in those cases where we usually in 2 dimensions, where we believe we've got some conformal invariant system like self-avoiding walks or something, and in 3 dimensions we get numerical estimates of critical exponents and growth constants and critical points. However, it always seemed to me that you should be able to do a bit better, and this talk really is about how you can do better and make some conjectures, and in some case refine those conjectures into a proof about the analytic structure of a whole class of problems that we encounter in this field. So by way of background and the sort of philosophy behind what I'm going to say, some of them, as we all know, some of the most famous results in mathematics prove intrinsic unsolvability. Squaring the circle is an old one, finding the roots of a general polynomial of degree greater than 4. And in physics we have corresponding results, including the impossibility of a perpetual motion machine, which doesn't prevent numerous such inventions occurring each year. In this talk, though, I want to address the general question of solvability of lattice models, and many problems in combinatorics and statistical mechanics, as you know, can be formulated as lattice models, and very few can be exactly solved. Those that can include the square lattice dimer problem by Castellane, Fisher and Temperley, Lieb's 6-vertex model, Baxter's 8-vertex model, Baxter's hard hexagon model, possibly the most famous one of all, the zero-field partition function of the 2-dimensional Ising model by Onsager, which really started the game, and subsequently the spontaneous magnetization of the 2-dimensional Ising model by Yang in '52. There are a number of simpler models which are also solvable, but yep.
When you say exactly solved, do you mean exactly as in Baxter's sense, or rigorously exactly solved?
Rigorously, I believe. I don't know whether people would haggle over some of Baxter's solutions and claim that they're not rigorous, but Alan, do you have a comment on this?
I don't know. I think some of Baxter's solutions may never have been proven to the satisfaction of mathematicians.
Well, Baxter himself says the hard hexagon model is exact but not rigorous.
Is what? Is?
Exact but not rigorous. There's some ansatz there that he doesn't agree.
These simpler models can definitely be proved, but most of them have strong geometric restrictions, such as directedness or convexity, which effectively reduce their dimension from 2 to 1. And they include a range of polygon enumeration problems, enumerated by both perimeter and area. These include row convex polygons, which are these little guys here. Row convex polygons, so-called 3-choice polygons. This is an interesting example. This is where after a north step you can go east or west, but after an east step you can only go north, and similarly after a west step you can only go south. So if you start here, you can produce these things with a big open jaw. Diagonally convex polygons, and the reason I emphasize these is, well, I'll come back to that later, but just remember what these are. 3-choice polygons. They were unsolved for quite some time. Staircase polygons, which are just 2 staircase paths that join at the top and bottom vertex, and are in one-to-one correspondence with the Catalan numbers, and convex polygons, which are convex in both directions. There are also walk models which are similarly constrained, such as spiral walks. The generating function for these is related to the partitions of the integers. We've got partially directed self-avoiding walks like these, or fully directed self-avoiding walks like these. These are all solvable. There are also a few animal enumeration problems, such as directed column convex animals and directed animals on the square and triangular lattice. There's also, of course, a long list of celebrated unsolved problems, prominent among which are the two-dimensional self-avoiding walks and polygons, two-dimensional percolation, two-dimensional directed percolation, the Q-state Potts model for Q greater than 2, directed animals on the hexagonal lattice, the susceptibility of the two-dimensional Ising model, which is semi-solved, the partition function of the two-dimensional Ising model in a field, and any property of the three-dimensional Ising model except for its dimensionality. Though, as a further aside, if you read the latest issue of the Philosophical magazine, you will find a solution of the three-dimensional Ising model in there. It's wrong.
Have you checked that it's wrong?
I know that it doesn't agree with the series expansions.
Okay.
So what do you mean by semi-solved?
I'll tell you that. Well, it's okay. I can tell you now, but I got a dot point. But
All right. I can wait.
Okay. So what do we mean by a solution? Okay. So ideally, one requires a simple closed-form solution, such as that known for staircase polygons, where you've got a nice algebraic expression. Less restrictively, you might seek a difference or a differential equation from which the properties of the solution might be extracted implicitly or explicitly. Thirdly, you might settle for a polynomial time algorithm to produce the coefficients in the series expansion of the solution. And it's in that sense that the Ising model susceptibility has been solved. In 2001, Orrick, Nicol, Guttmann and Perk gave a polynomial time algorithm for the coefficients, used it to generate more than 300 series coefficients, and then analysed the structure from the generating function. And we've now, just because we can, we've now got 2,000 terms. And we're writing.
Did you learn more about the structure?
There's a big paper under construction which has several authors, all of whom seem to disagree. So it might take some time to actually.
Because there seem to be some interesting unknown things about the correction to scaling properties.
What we'd really like to do is to do it on another lattice, but we don't have the machinery.
Is that the paper for which you need the French translation?
Beg your pardon?
Is it the paper for which you need the help of French translators?
Yes,
or something?
yes.
Oh,
Okay, so here I want to show you how to conjecture and then in some cases prove, the prove part being based on the PhD thesis work of Andrew Recknitzer, who was a student of mine who also spent a year in France working with Mireille Bousquet-Malou, that the above list of unsolved problems, as well as a bunch of others that I haven't mentioned, like bond animals, bond trees, and directed bond animals, cannot have solutions that belong to a certain large family called differentiably finite functions, which I shall define in a moment. And by a solution, I mean a closed form for the generating function, the coefficients of which enumerate objects. For example, Cn might denote the number of objects of a certain type with n bonds, number of self-avoiding walks, number of percolation clusters with n sites, that sort of thing. We write the generating function in the usual form, where this is a curious notation for which I take no particular credit. That should be a z, and z can be a multi-dimensional variable. F can be a function. It's amazing how you can read a seminar presentation several times and not see something, and then when it comes up on the screen, it sticks out like the proverbial. So anyway, so this is of course f of z is c n z to the n. F can be a function of several variables, such as the area and perimeter in the case of polygons, or field and temperature in the case of a magnetic model. So what do we mean by d-finite function? If f is a formal power series in x, where x in fact can be a function of several variables, f is differentiably finite or d-finite if there exists a dE of linear DE with polynomial coefficients of this form, where the pk, as I say, are polynomials in X. So in the space of all possible functions, you've got your rational functions here, which are a proper subset of algebraic functions, and these are both proper subsets of D-finite functions. And then, of course, we've got all power series, which D-finite is only a subset of. But these certainly contain, D-finite functions contain all algebraic and rational functions.
So D stands for differential.
Yes, differentiably finite, or holonomic if you prefer.
What means finite here?
Finite ordered differential equation.
Yeah.
Not infinite.
Yes, this is exactly. This is. So if these unsolved problems did have D-finite generating functions, we could compute the coefficients of their generating function Cn in polynomial time, because it follows from the differential existence of those differential equations that you can construct a recurrence relation which you can then iterate in polynomial time. Most of the solved models that I showed you on the first transparency, the Onsager solution, the Baxter solution, etc., have D-finite solutions.
But things that are not D-finite but are solvable are things like, given in terms of Q series.
You almost, yes. I know of no exception to that.
You mean that in order to compute the coefficients in polynomial time, you need to have a bound on the degree of the polynomials and on the overall degree?
Not necessarily, but there are also, if you have a D-finite solution, you can automatically convert that into a recurrence, a linear recurrence of finite degree, and then you can iterate that in polynomial time.
Or you have to know the differential equation.
Yes.
What is this?
That's what I said. If they did have the generating function, and we knew it.
Especially if you guess that there is a recursive relation which goes back in memory up to, say, 5 steps, and
Yes.
it's no higher than cubic, something
Yes.
like that, and you have a bunch of coefficients,
Yes.
you can fit for all the
Yes.
coefficients
Yes.
and find that.
Exactly.
But you must know in advance, even if not the differential equation, at least that it has bounded such and such.
Correct. Yes, and in fact, that's you are anticipating what I'm going to do. So, well, that's exactly what we're saying here. So, based on this observation, a legitimate and effective method to try and solve such a problem is to generate by counting the first few terms of the power series and then look for the underlying differential equation. That is,
few means a few hundred.
It varies. I mean, you can do it with something like 20 terms. We could have found the Yang solution for the magnetization. With something like 30 terms, we could have found the Onsager solution for the free energy. But in some cases, you do need a few hundred. For example, those 3-choice polygons, by using the methods that I'm about to show you, we conjectured that that was differentially finite. Then, using the observation that I made in my seminar last week that I learned from Hammersley, that once you know there's a solution, it's a lot easier to find it, we devoted resources to expanding the series. We said there must be an underlying DE. And we got more and more terms, did more and more work to get more and more terms until we found the DE. Now, the DE turns out to be a swine of a DE. It's a 7th order ODE with polynomials of degree 30 something. So we needed nearly 300 terms to find the ODE, and that's the minimal order ODE. Of course, the DE is not unique, but that's the one of minimal degree. And so if we didn't know that there was such if we didn't have really strong belief that there was such a solution, we would never have embarked on such a stupid project as to generate 250 terms of this series to find it.
And then you proved the thing was correct?
Andrew Rechnitzer claims he has a method whereby you can prove it's correct, but it's a horrible problem, as you can imagine, with a DE of that size. Our quasi-proof is that we then got a better algorithm for generating the coefficients. We generated 1,000 coefficients, and if our DE that we find using only 250 produces the next 750 correctly, the chances that it's wrong are remote. I would bet my house on it even, not just yours. Using the SoCal test for confidence in one's results. Okay, so just to give you a bit of familiarization with these differentially finite functions, note that most of the special functions of mathematical physics, such as the hypergeometric functions, are D-finite. The gamma function is a notable exception. Most of the techniques we have for guessing generating functions look for D-finite functions. There's this well-known piece of software to those who know it well called GFun, which is part of Maple, which enables you to find underlying differential equations from a power series expansion. And once one has a conjectured solution, it's much easier to prove that it's correct. So let's have a look, just put this in the picture. The objects we're trying to look at, polymers or whatever, even if they live in R3 or R2, we usually of course simplify the model so that we can apply statistical mechanics and combinatorial techniques. So we stick it on a lattice. And by sticking it on a lattice, we embed them usually in Z3 if they live in R3. So that a polymer becomes a picture on a grid made up of elementary pieces of a graph, depending on whether you're a mathematician or a physicist. We've got vertices or sites, edges or bonds, faces or cells, as illustrated here once we've embedded this object, in this case in Z2. I'm going to look at bond animals and self-avoiding polygons now. So a bond animal is a finite connected union of bonds on the square lattice, and it's defined modulo translations. And we're interested in how many of these there are. So similar definitions hold for site animals, polyominoes, polygons, etc. In this talk I'll concentrate on bond animals, and if we start asking how many can be constructed using n bonds, denote this number C subscript n, and knowing Cn of course gives the generating function. So if we start counting, C1 is 2, we can place a bond vertically or horizontally. C2 is already 6, there they are. And we can answer this by hand if you're enthusiastic, up to about 8. Better use a computer to count them all. The number grows exponentially, and it grows like a lambda to the n, so that the time taken, if you simply count them directly, also grows exponentially, where typically lambda is between 2 and 10. And what this means in practice is that if lambda is bigger than 2, it means that the amount of computer time that it takes to count one more is more than the computer time that it took to count all the previous lot. So you're on a hiding to nothing, even with Moore's law helping you with these values of lambda. So any method that is quicker than this would be good, and arguably a nice solution would be a closed form and easily computable expression for Cn, or a similar expression for either the generating function or the exponential generating function.
Are the lambdas known? The lambdas, are they known for various lattices?
Not the answer is in some cases. So for example, in the case of the Ising model in 2 dimensions on the square lattice, we know that lambda is 1 plus root 2. But that's exceptional. I mean, this is in the case of self-avoiding walks, that's the growth constant. We know that from Nienhaus's conjecture in the case of the hexagonal lattice, and we have good estimates why I say good estimates, 9, 10, 11 digits for the other lattices, but we don't know them exactly usually, no. And we certainly don't know them in 3 dimensions, except numerically. So for example, in the case of 3-dimensional self-avoiding walks, it's about 4.6. So an algorithm or recurrence that computes Cn efficiently, preferably in polynomial time, is what we seek. So to give you an example, here's an utterly trivial example. If we want to count rectangles by perimeter, a solution of the form that the number of rectangles of perimeter n is the sum over 1 over the set of rectangles is true, but not terribly helpful. Whereas a solution of this form is rather better. We calculate the generating function. We get a x to the 2a plus 2b. where a greater than 1, b greater than 1, and we can trivially sum that to get this expression. That's more informative, especially if you can invert it to show that R2n is n minus 1. So that's what we'd like to be able to do, but of course in most cases our problems are slightly more complicated than counting rectangles. For most of the lattice models we're interested in, we can't do anything like this. So here we've got bond animals, which we'd like to do, bond trees, self-avoiding polygons, self-avoiding walks, and directed bond animals. These are all unsolved. Currently, the best solution for generating coefficients of this class of model is still takes exponential time, but less than lambda to the n. This solution is based on the so-called finite lattice method, which was first developed by Ian Enting, was subsequently refined in joint work by Ian Enting and me, and then me and Ivan Jensen, and now Ivan Jensen has sort of taken it over and keeps refining it more and more. It is still an exponential algorithm, but exponentially faster than the brute force algorithm I was outlining. So to give you an idea of the sort of improvement one can obtain, if you look at square lattice self-avoiding walks or polygons, takes time lambda to the n with lambda about 2.638, whereas Jensen's best algorithm has reduced the lambda to about 1.2. So of course for the same computing resource you can go vastly further. I haven't got time to go into the way that the algorithm works, but it would only be fair to say that it has a downside, which is that if you have direct counting, the amount of memory you need is linear, grows linearly with n, whereas for this algorithm, this smart algorithm, the amount of computer memory that you require also grows as lambda to the n. So in the early years when memory was really scarce, the impediment to our computations was not time but memory. But as I like to say, you can buy memory but you can't buy time. So we were able to overcome that with money. And indeed, Alan...
Time is money.
Can you prove that?
Well,
That's the advantage.
for parallel algorithm,
Money is not.
for parallel algorithm, time is also money.
Yes, yes. Yeah, well, we do everything. I mean, we parallelize it. We run it on, 10,000 processors and et cetera, et cetera.
So the animal problem seems just as complicated as a self-avoiding polygon.
Yes.
That's not obvious, right?
Well, maybe not, but all these problems are equally horrible in terms of trying to solve them. Yeah. And we can get similar improvements for other models. However, as I remarked, despite lots of effort by lots of people over many years, there are still no really nice solutions to the above problems. And as I mentioned, the polynomial time algorithm for the two-dimensional Ising susceptibility is an exception. There are possibilities. Baxter developed an algorithm which we think is sub-exponential in time, but nobody's even proved it, which is the corner transfer matrix method, where it is conjectured that the computational complexity goes like e to the beta root n, but as I say, this hasn't been proved. It's just based on extrapolations of times with n.
And implemented it.
It's been implemented, yes.
And does it end up being better than the finite lattice method after a certain point?
The answer to that is we don't know, because it falls apart beyond a certain value of n. It relies on, it's only been implemented successfully for one model, which is I think the hard squares. Or if you try, I actually had a very good PhD student working on this project, and a number of us, Ian Enting and I and others, all kicked in when he ran into difficulties which we initially thought were due to lack of ability or experience on his part, but turned out to be, as far as we can tell, an intrinsic difficulty with the method. It seems to be almost lucky that it works, and it only seems to work as far as Baxter pushed it, and we sort of pushed it one or two values of n further, and then it falls apart. You require certain properties of matrices to hold that only hold for finite values of n, and beyond, for n bigger than that, it no longer holds, and you can't find the eigenvalues, or
So it's not really an algorithm.
no.
It's funny to say that it has some exponential time if n can't go beyond 36.
Well, I still don't believe that it's hopeless. I think there's it's a problem waiting for a good idea. That's not to say there is no other rigorous work. Of course, there's a lot of, we know that this limit, as I mentioned last week, exists. We've known that for 50 years, so we know that this growth constant lambda exists. Rigorous bounds on lambda can be found. There's also a large body of numerical and not entirely rigorous work that has greatly improved our understanding of the behaviour of these models. What I want to show for the rest of this talk is how to conjecture and then outline how Rechnitzer proved that bond animals, bond trees, self-avoiding polygons and directed bond animals cannot have D-finite solutions. So there's not a lot of point looking for them. Of course, if they did, we could generate the coefficients in polynomial time. So how do we prove non-definiteness? Okay, our first theorem, a D-finite power series has a finite number of singularities. So to give you an example of a function that isn't D-finite, the generating function of partitions of the integers has this well-known expression. It has singularities on the unit circle, which become dense on the unit circle. It's not D-finite. Unfortunately, for the problems at hand, we know almost nothing about the generating function, so otherwise we wouldn't be trying to solve them. We don't even know the location of the dominant singularity, which is equivalent to this lambda.
So Tony, what precisely is meant? I mean, a D-finite power series, it has some finite radius of convergence, I guess.
Yep.
But then you're saying that it has some analytic continuation to some Riemann surface that has a finite number of branch points, or some finite impulsive branch points? Or?
Well, it's got to, because if you think of the structure, you've got a finite degree polynomial. The singularities come from the zeros of the polynomial multiplying the highest order derivative.
Oh, I see.
And also this one is especially easier somehow because within the circle we can reach the singularities really all on the edge,
Yes.
a non-countable one all on the edge. If they were a non-countable set far away from the boundary, they would be maybe technically harder to see them.
Possibly, yep. I want to say nothing about this except to give you an example of a non-definite function. I'm not interested in its structure.
The gamma function is another.
Yeah. As I say, for the problems at hand, we know almost nothing about the generating function. We don't even know the location of the dominant singularity. But my point is that, yet another example, if you try and make the problem a bit more complicated, you can prove something. And what we do to make it more complicated is to make it anisotropic. That is to say, we distinguish between the horizontal and vertical bonds, as I've done here. And for those of you that are colourblind, the horizontal bonds are blue and the vertical bonds are red in this picture. And then I go from a one variable generating function, if I'm counting these by perimeter or number of edges, to a two variable generating function where x carries is conjugate to the number of horizontal bonds and y is conjugate to the number of vertical bonds, and CNM just denotes the number of these objects with n vertical and m horizontal bonds. As I said there. The point about the reason for doing this is that the anisotropic generating function cuts the system up into smaller, easier pieces. So if I write this now in this manner, sum over m, then hnx is just the generating function for objects with precisely n vertical bonds. And it can be proved that this is a rational function, and we can compute the first few exactly. Quite trivially, just where's the chalk? If we're looking at these animals, then the simplest case is h0, and if we ask for the generating function h0x, it's just x over 1 minus x, because you can have something with 1 bond, with 2 bonds, with 3 bonds, etc. So, as I say, we can compute the first two exactly. There's the first one. And we have the following theorem, that if we have this generating function expressed in this manner, so it's an anisotropic generating function. For most families of bond animals, and I'll make that more precise, these generating functions, h and x, firstly, they're rational. Secondly, they have numerator degree less than or equal to denominator degree. And most significantly, they have a denominator that is the product of cyclotomic polynomials and nothing else.
And you can say for each n exactly what the denominator is?
Yes.
So the only non-trivial thing is to compute the numerator.
Yes. So if we write hn as a rational function like this, the denominators are the key to the singularity structure, of course, and the cyclotomic polynomials, just to define that for those of you who have forgotten or whatever, the cyclotomic polynomials psi subscript kx are the factors of the polynomials 1 minus x to the n, and in particular we write 1 minus x to the n as the product of cyclotomic polynomials psi k, where k is a divisor of n. So psi 1 is 1 minus x, psi 2 can be divided as a product psi 1, psi 1 minus x squared rather can be expressed as the product psi 1, psi 2, 1 minus x cubed can be expressed as psi 1, psi 3, 1 minus x to the fourth, psi 1, psi 2, psi 4, and so on, psi 5, psi 6. So let us look at a few solved models. For directed walks, the denominators take this very simple structure. They're just the psi 1 to the power n plus 1 for the denominators. For staircase polygons, we have psi 1 to the power 2n plus 1 as the denominator. For these three-choice polygons, we have psi 1 to the 1 power, which is something like, it depends on whether n is odd or even, which is why I've written it this way. But this is a simple function of n, like 2n plus 1 in the odd case, and I don't know, n minus 1 in the even case or something, and bn is similar. So we just have psi 1 and psi 2, and it was this experimental observation that convinced me that this problem should be solvable, which is why we then went ahead and ground out the coefficients. So we see that the denominators in these solved cases only involve the first cyclotomic polynomial or products of the first two. And this is just an observation that this is a characteristic of solved models. We'll also see that most unsolved models have denominators that comprise products of cyclotomic polynomials of steadily higher degree as n increases. So this really splits the problems that we can solve and the problems that we can't solve into two classes. So for example, if we look at self-avoiding polygons based on our numerical work, we find by exact enumeration that these are the denominators. So you start doing this and you think, oh, this looks terrific. And then you get to D5 and you start seeing psi 2 appearing, but you're not too worried about that until you then get to 7 and you see psi 3, then psi 4 coming in at D10, and it just builds up, so you get this sort of implacable build-up of higher and higher order cyclotomic polynomials appearing in the denominator.
But with beautiful exponents.
Yes, you can predict the exponents. You can predict the whole structure of the denominator. So all you have to do now is predict the numerator and you have solved the problem.
You have a conjectured closed form expression for the denominators,
Yes.
but not proven.
Yes, we have a proof in some cases as well. So way back in '96, Ian Enting and I made the observation based on these sort of numerical experiments that solved models have simple denominators and unsolved models have poles that become dense on the unit circle. And we suggested this as a test of solvability in some sense. The notion of solvability can be made more precise in that a d-finite power series cannot have this dense pole denominator pattern. Here's the theorem due to Bousquet-Milou, that if we write our two-variable generating function in this manner, be a d-finite power series, let S be the set of all singularities of the HNs, then the set S has a finite number of accumulation points. Otherwise it can't be d-finite. So as you can see, what's happening as we get more and more cyclotomic polynomials, you've got more and more accumulation points on the unit circle, and this immediately destroys the possibility that the generating function is d-finite.
So it is the case that they all live on a unit circle and not scattered away.
Yes, the HN denominators, yes.
So in a kind of canonical in a kind of microcanonical ensemble in which you have just a given rational function, but with a bunch of cyclotomic polynomials, you would see that there are these quasi-singularity really on the circle and not on a line like
Yes.
in gamma.
Yes.
And you can see, well, okay, this
Well,
is helping a lot.
this is what? Helping a lot? Not enough. Well, not yet anyway. Anyway, so for the unsolved models we've investigated numerically, this build-up of denominator zeros leads us to conjecture that they become dense on the unit circle, and hence that their anisotropic generating function cannot be d-finite. Now there's another thing here I should point out. It is a theoretical possibility, though of course no one who studies any of these problems believes it, but we don't have I should point this out. What we're doing is, for the anisotropic case, you might argue that, okay, well this is a feature of anisotropy. If you've made the x and y weights different, if you make them the same, you may lose all this, and it might be really nicely behaved. And I mean, you can see this. It's trivially easy to construct a function that behaves that way. D-finite, a d-finite function plus x minus y times a non-d-finite function. And then in the isotropic limit, it's d-finite. Though, of course, anyone who's had any experience with these lattice models is confident that that's not the case. But I mean, that's not a proof. Okay, I'm just pointing out that if what I'm talking about is very much about the anisotropic generating functions. And yes, as I say, a d-finite power series cannot have this dense pole denominator pattern. If you look at all the solutions that we know, such as the Onsager solution or the Yang solution, which you can solve for the anisotropic case, all that anisotropy does is to move the singularities in the physical situation around in the complex plane a little bit. It just changes things slightly. It doesn't change any of the underlying physics or any of the underlying asymptotic behaviour. So I don't believe that when you go from anisotropic to isotropic, things change dramatically. But
do you have any examples of solvable models where you have more than two, but yet a finite number of cyclotomic polynomials?
no,
It's either 1, 2, or infinity.
that's the observation, yes. So what Andrew Rechnitzer ended up proving is that the anisotropic generating function of bond animals, bond trees, self-avoiding polygons and directed bond animals have singularities that form a dense set on the unit circle, and hence these functions are not d-finite. A secondary result is that for most families of bond animals, the denominators of these polynomials hnx are bounded in the sense that dnx is a divisor of this product of cyclotomic polynomials psi1 to the 3n plus 1 times psi k. So you can see where the higher order k's enter. They enter as you increase n in this way, k equals 2 to the floor of n over 2 plus 1. Whereas for self-avoiding polygons, the denominator is a divisor of this. These bounds appear to be very tight. For bond animals and trees, the bound is probably exact, and for self-avoiding polygons, the bound is out by a single factor of 1 plus x. This is just an artifact of the fact that in one case the numerator has a 1 plus x in it, which cancels with one of the psi 2 1 plus x factors in the denominator, which is why it's not an exact bound.
And if you, instead of writing the denominator in terms of cyclomatic polynomials,
Yes.
you really want to write it in form 1 minus x to the k to some power h.
Yes?
Maybe at the price of adding stupid factors in the numerator. They will be ugly formulas, so they will be nice.
You mean you want to take out all the other cyclotomic polynomials from the denominator by multiplying?
I don't want to have isolated cyclotomic, but only 1 minus x to the k factors. This will be an ugly formula, or they collect out.
I see what you're saying. So it looks nicer in terms of cyclotomic polynomials than in terms of 1 minus x to the k's. The pattern is more obvious. But there's no reason why you can't, as you say, there's no reason why you can't rewrite it like that. And as Alan points out, this determines half of the unknown anisotropic generating function. We know the denominator, we just need to find the numerator. Unfortunately, these are much harder, and you'll see why. So these results are obtained by squashing animals, or what Rechnitzer called haruspicy. Haruspicy, if you look it up in the dictionary, is telling the future by examining the entrails of animals, which people did in the Middle Ages. And
Not before, the Romans and the Greeks.
oh, okay.
Not the average.
Oh, even earlier. All right. So, well, we're revisiting this technique. So, consider firstly animals with 0 vertical bonds, which is the one I've just mentioned here, G0. Here they are. Any animal in this set can be squashed down to a single bond by just bond deletion, as we've shown here. Here's find a bond, delete it, close up the animal, and you go from a 5 animal to a 4 animal. And you can also reverse this by bond insertion. The single horizontal bond is minimal under squashing. Sorry, there should be a space there. The other animals in G0 come from it by unsquashing, and more generally, we cannot squash or expand bonds as we like. We can in this case. We have to preserve the topology of the configurations, preserve self-avoidance, because we want to make this a reversible operation. So we want to be able to expand it and get back what we want. So we need a couple of definitions. A column of an animal is characterized by the horizontal bonds within a horizontal lattice spacing. So if there are k horizontal bonds in the column, we call it a k column. And you can see here we've got a 4 column in this particular figure because there are 4 horizontal bonds. When 2 neighbouring columns are duplicates, we're able to remove one of them. So here we've got 2 4 columns in this animal. We can remove one of them and squash it down and just be left with one. And this is now the minimal animal of this type.
But you mean duplicated, and you can have vertical bonds or without vertical bonds in between?
Sorry, I'm not sure what.
You have 2 identical columns of horizontal bonds.
Yes.
In between them, there are arbitrary vertical bonds or no vertical bonds.
No, in this case, you have no vertical bonds.
But is that a general feature
Yes.
when you do this?
Yes.
So you have 2 identical columns with no vertical bonds in between.
Yes.
Then you can do this.
Yes.
Yeah.
So an animal that can't be squashed further is a minimal animal. We saw that there's only one minimal animal where there's 0 vertical bonds. There are, in fact, 16 minimal animals when there is 1 vertical bond. Here they are. So G1 has 16, and the number grows quickly. But notice that these GNs have a finite number of minimal animals, 1 in the case of G0, 16 in the case of G1, but an infinite number of non-minimal animals. Also, it's not possible to reduce an animal to 2 different minimal animals. We can reduce this, all these reduce to the same animal. This gives an equivalence relation. 2 animals A and B are equivalent if they reduce to the same minimal animal. And the equivalence relation partitions Gn into equivalence classes. where we have, for Gn, we have a bunch of different pieces corresponding to the different minimal animals that occur within Gn. We'd have 16 of these pieces in the case of G1. We'd only have 1 in the case of G0. So the minimal animal contains all the information needed to produce the generating function of the equivalence class. We can squash the minimal animals down we can squash our set of animals down to minimal animals. We can take our minimal animals and expand them out and recover the generating function. So if, to see how this works, here is an animal, a minimal animal. We want to be able to expand this arbitrarily. So this gives us a factor x squared 1 minus x squared. If we extend this out by another 2, you can see you pick up an extra factor of x squared, and this will give you x squared, x to the 4th, x to the 6th, etc. as you push this out further and further. This 3 column gives you a factor x cubed over 1 minus x cubed. You can add 3 columns here. This 1 column gives you an x over 1 minus x, and this 2 column gives you an x squared over 1 minus x squared. So you can see by deconstructing the minimal animals, you get factors of this form for all the minimal animals. So if A is a minimal animal and gamma k of A be the number of k columns in A, then the generating function of all the animals in the equivalence class of A is just given by this generating function is just the product over k, x to the k, 1 minus x to the k to the power gamma ka, as illustrated in this example.
Clear, so that you just show your subfamilies of minimal animals which have the appropriate denominators because you're summing all of them and
Yes.
you prove the denominators are there.
Yes.
Okay. This is super general.
Yes?
You can do with a Guttmann model.
You can do it?
With a lot of models.
Yes, yes, absolutely. So we can write Hn as a sum over the minimal animals in G. It's just each generating function is of the above form, and we just sum over all the minimal animals. And there's our Hn. And now you can see why the numerators become so complicated, because you're adding sums of products, and so you can see what the structure is. It's polynomials times cyclotomic polynomials added together, so it gets messy. So for any given n, the number of summans is finite, and so we have the following theorem, that if P is the anisotropic generating function of a set of animals G, then H is a rational function. The degree of the numerator is the degree of the denominator, and the denominator is a product of cyclotomic polynomials. So that the previous demonstration that I gave you can be used to prove that. We can also see which singularities are caused by which minimal animals. So this is how we're working slowly towards a proof of all this. If the denominator of H contains a cyclotomic factor psi k, then there exists a minimal animal A in Gn such that A contains a k column. You can only get you've seen that psi k crops up when you get a k column. And if it takes at least V vertical bonds to build a bond animal with a k column, then the denominator dnx contains no cyclotomic polynomials psi k, of course, if n is less than v, because there's just not enough vertical bonds to do it for you. Similarly, multiple k columns give multiple factors of the cyclotomic polynomial psi k. That's the idea behind the proof of the denominator bounds. Unfortunately, when can there be a factor of psi kx raised to some power alpha? That gives you an idea. How many vertical bonds do you need to make alpha k columns? It's not quite as simple as I've outlined. It's complicated by the fact that you need a finer equivalence relation than simply column deletion. If you look at this example, the point is that horizontal bonds in something like this can be squashed or expanded independently of each other. You can expand that one without doing anything to that. And then while you've got a 2 column here, you've only got a 1 column there. And so you have to be a little bit more careful than just expanding things independently. So to prove the non-definitedness, we study those animals that cause the first occurrence of psi kx, the first occurrence of this cyclotomic polynomial. And these seem to have simple patterns. For self-avoiding polygons, a new psi kx enters in H3k minus 2x. And these poles are caused by so-called 2-4-2 polygons. 2-4-2 polygons are things where you have this pattern 2-4-2 vertical bonds as you go down. 2-4-2. If you cross here, and here's a 2-4-2. And for
What is the pattern? What is the pattern?
as you cut horizontally, you need enough vertical bonds to build these K columns, right? And these the minimal polynomial, two edges that you cut here, 4 edges that you cut, 2 edges. For the animals like this, a new psi k enters first in H2k minus 2 when you've got just 2 animals. So you've got 2 vertical bonds in each row. And bond animal denominators are caused by 2 animals, as you can see in the next slide. So here we've got a 1 minus x in the denominator, as we've just seen, and this here it is explicitly. D1x, you've still only got the first cyclotomic polynomial. The first occurrence of psi 2x occurs in this guy, where you can expand this, and you can see this is the first 2 animal we've got. Then this is the next. We still don't get another 2 animal at D3 with this kind of structure. That only comes in at D4, where you'll get 3 columns. And so here for this particular animal, you pick up a factor 1 plus x squared cubed. Similarly, it's like Fermat's last theorem. My margin isn't large enough to contain the proof in this particular case, but you can see that with 1, 2, 3 of these, you'll get a 4 column, which gives you a 1 plus x squared to the 4th. The denominators in the case of self-avoiding polygons similarly are caused by 2, 4, 2 polygons. This is 2, so that's where you get a 1 minus x. This is the first 2, 4, 2 that you can draw, which only comes up at D4, and you pick up a 4, a psi. We're working in, because you've got an even number of terms, you pick up a psi 2 here, and you'll pick up a psi 3 here, which is this guy here. So this allows us to split the HNXs into 2 parts. You'll have one part that has no psi kx, and you'll have another part that has some psi kx's in it. And for self-avoiding polygons, this becomes, in particular, an animal which is not a 2-4-2 type, a polygon which is not a 2-4-2 type, plus polygons which are 2-4-2 types, which have n vertical bonds. Then, when we add the A's and B's, all the psi k's come from the B's, so we don't, and if there are any cancellations in the H's, they also come from the B's. We cannot compute AN, however we can compute BN, and since all the interesting stuff comes from the B, this is rather fortunate. For self-avoiding polygons, this means counting all the 2-4-2 polygons, and for the bond animals it means counting the 2 animals. And we use the so-called Temperley method to do this. We build the animals row by row, we sort of stick them together and delete duplicated rows, and so come up with something like this. This method, the original idea goes back to a paper of Temperley in 1956 and has subsequently been used or rediscovered by Klarner, Bousquet-Melou and many others. The enumeration of this sort of thing gives rise to some fairly ugly functional equations that look like this. You've got 6 partial derivatives here which have to be evaluated at s equals 1 in principle. You've got some other function of sx and y, and you've got this function C8 of f sx xy. Now,
S is this catalytic variable? Or
yes. That's right. Exactly so, because it disappears. You'll see what S is in just a moment, because I'll give you an example. This is the generating function of the 2, 4, 2 polygons, and even this is pretty horrible. The CX's are rational functions of S, X and Y. You can't in general solve such a functional equation. Their expressions for the CK are very much not nice, lots of pages of maple for each one. Thankfully, though, the only term that's important is this last one, this C8. So you've got the structure of this is f of sxy goes to f of sxxy. Because what that does is it adds a bond. The term fs sxxy is the only one in the functional equation that introduces new singularities. So what we've got is if we've got some polynomial over 1 minus sx to the k, and we make the substitution s goes to sx and we iterate, we'll get some other polynomial over s 1 minus sx to the k plus 1. And when we said s equals 1, you can see you've got a higher order cyclotomic polynomial. So it's only that factor in the functional equation that does horrible things to you. So it takes factors of 1 minus sxk and makes new factors of 1 minus sx to the k plus 1. And analysis of this term then shows us that the new psi kx appear where we expect them to. That is to say, for self-avoiding polygons, a factor of psi kx appears at h3k minus 2x, and for animals it appears at h2k minus 2x. And you can also prove that there are no cancellations. For self-avoiding polygons, this has, of course, singularities at psi kx equals 0. Likewise for h2k minus 2 in the case of bond animals.
By no cancellations, you mean that the
numerator can't cancel the denominator. So, because one way that you could say, well, how do you know that they continue to build up? You might get cancellations in the numerator. And you can prove that you don't.
From this functional equation. So in a certain sense, this subset, these 2 for 2 polygons, are exactly solvable in some sense or other.
In some sense or other, yes. But I can't write down the generating function.
But you can you can say that the generating function is some explicit thing plus some other stuff that you know has different singularities?
Yep. So we can conclude that the set of all singularities then in these HNXs is dense on the unit circle, and therefore the anisotropic generating functions are not D-finite. And the full details are available in a couple of papers by Andrew Recknitzer. So where to from here? Well, we still haven't quite managed to make it work for self-avoiding walks. Again, my vanishing PhD student John Dethridge, of whom I spoke last week, claimed to have proved this, but then vanished before he wrote up the proof. We would also like to apply it to magnetic models such as the Q-state Potts model, make it work for site animals and polyominoes, ask more general questions. Given that we know so much now about the structure of these things, can we somehow make it help us with series expansion techniques? Is there anything we can do to find out more information about the numerators? And given that what we've really done is to show that these things are not D-finite, well, there's a huge gap between D-finite and all formal power series, and we know that there are models that can be solved that are not just D-finite, some of those with 2 catalytic variables that come up with Q functions that Alan mentioned earlier and that I spoke about briefly last week for certain types of prudent polygons. And I think Xavier made some remark last week along the same lines, suggests that we really should be looking at trying to refine the space between d finite and all power series into something finer and see if we can classify the sorts of functional equations or generating functions for which we can realistically expect to find solutions and those that as yet we still can't. Thank you. That's just
Maybe this appearance of the catalytic variable as here and there suggests something like there could be maybe another catalytic variable such that the true function is when this variable t, say, is equal to 1. But when t is equal to 1 over x, well, maybe t was appearing with appropriate powers in the denominator such that they all become small cyclotomic polynomials. Because instead of having 1 minus x to the k, you was exactly having 1 minus t to the k minus 1 x to the k. Just if one introduces another catalytic variable in the recursion in such a way that every time that you increase x, you also increase t. So there will be some function in a larger space such that in a subspace it is truly definite, and the real point is somewhere else, not far somehow.
It sounds possible. It might be worth experimenting with some really simple model to see if that approach produces anything.
Can you say what is your catalytic variable S?
You wrote f of sxy, but you didn't say what s was.
I'm sorry, I don't recall. It's probably something like, well, to give you the idea of the sort of thing that happens, if we're looking at, say, at prudent walks that end, say, here or here, then typically the catalytic variable is the displacement along here and the displacement along here. So you've got two catalytic variables telling you exactly where you finish up. And when you look at the total generating function, you don't care about these. But you need that to count those particular guys, and then you just set that variable equal to 1. So it's something like that.
You mentioned how making the thing anisotropic was very helpful.
Yes.
So would it make sense to further refine this? Like, for instance, distinguish between consecutive vertical bond or something. Could that help you perhaps in doubling the number of terms you can generate or something?
I don't see how, but I'm happy.
Or maybe this is a very simple way of introducing another parameter, but who knows? Maybe.
There are other advantages of making things anisotropic, which, if for example, you take the Ising model, free energy, you can. If I write the free energy, I can write the free energy. Of course, I've got a symmetry. But there's also an inversion relation for the free energy, which I don't remember exactly, but it's something like f of x 1 over y minus psi of minus xy is log 1 minus y squared. It's not exactly that, but it's something similar. And you might ask, well, what is 1 over y? It's some appropriate analytic continuation. Now, the point about the existence of this symmetry relation plus this inversion relation is that these psi xy p. It turns out that these so what am I? If I write psi xy. Where's the eraser? If I write my psi xy in exactly the same way as sum over hn y to the n, then these hn y's are of the form a polynomial of degree 2n minus 1 with a denominator involving just the cyclotomic polynomial y equals 1 minus y rather. These polynomials are both of degree 2n minus 1, so there are 2n unknowns. This symmetry relation cuts those 2n unknowns down to n. This inversion relation allows you to determine those n coefficients. So the existence of the symmetry plus the inversion relation and this observation, numerical observation that this is the structure, or you can say take the Onsager solution and see that this is the structure, but if you were doing this numerically, what I'm saying is that these two relations plus this observation would have been enough to determine the Onsager solution automatically without having to do all the work that Onsager did. And similarly, you can do exactly the same for the free energy, for the magnetization. And there's a similar set of symmetry and inversion relations that exist for the susceptibility. And if you try and do it for the susceptibility, you get very excited because you find this structure for n up to 9. And only at h9 does the second one start to appear. And then only at h16 does the next, they appear at order n squared. So, you know, if you're only doing low order numerics, you get very excited and think that here's a way to solve the Ising model. And in fact, there's a nice connection for those of you that are familiar with the details of the Ising model. It can be expressed, the susceptibility of the Ising model can be expressed, as was shown by McCoy and co., in terms of sums of contributions of n particle susceptibilities. That is to say, we can write the susceptibility at the high temperature susceptibility in terms of these contributions. So and there's a connection, but which I've never quite understood, this particle notation. But the point is that the different psi's that enter correspond to the different cyclotomic polynomials that crop up. If you just take psi 1, which is in fact algebraic, that's what corresponds to the fact that you only get the first cyclotomic polynomial when you play this game with the susceptibility. And it's only when psi 3 kicks in at order v to the 9th that you pick up this the second cyclotomic polynomial, and so on and so forth. So there's a nice connection between the underlying combinatorics and this somewhat obscure representation of the susceptibility.
And for all of your different algorithms for producing these series, the finite lattice method and so on, it's basically no more work to produce the anisotropic one instead of the isotropic?
It's no more work, you need more storage, obviously. And that's the limitation. You know, these things, some of these things take gigabytes to store. Yep.
But, I'm not sure this is a very well posed question, but it seemed to be an important constituent that when you look at the anisotropic model, there were only, for each particular value of n, there were only a finite number of minimal animals.
Yes.
And that to me kind of sounds like good news. Bad news would be that there were an infinite number.
Oh, if they're infinite number, we couldn't do it.
Yeah. So for the models that you do solve, that are solvable, what do the minimal animals look like? Are there a bounded number?
Yeah, for each value of n, there's a finite number.
But for the ones that you can't solve,
I think for any for the whole idea of this equivalence class is that I don't know, I can't think of for this whole approach to be useful, that there's got to be only a finite number of minimal animals. Otherwise, there's no point in doing what we're doing.
But I think what he's asking, do the solvable models have fewer minimal animals at each order? Or what distinguishes the solvable ones from the unsolvable ones?
Are there fewer? I don't think there are fewer.
It's not that they're fewer, but it's that for the solvable ones, this finite set of minimal animals does not produce growing cyclotomic polynomials in the denominator.
That's right.
Whereas for the unsolvable ones, they do, and you can prove they do
Yes.
by extracting the bad minimal animals.
Correct. Yes, I guess if you look at the objects that you can get from the solvable models, I mean they are structurally simpler, and you don't have this complication with k rows and k columns. Making them bigger doesn't make them more complicated.
Somehow you were telling at the beginning that solvable ones are morally either convex or quasi one-dimensional.
Yep.
In both cases.
The minimal
If
animal
they
is
are
much simpler.
convex, somehow
Yeah.
k is always more or less
Yep.
2.
Yep.
If they are one-dimensional,
Yep.
it's
Exactly.
always more or
Yeah.
less.
Yep.
So this is bounding
Yeah.
k.
So there are. Yeah. So the answer to your question is yes. There are fewer, necessarily fewer, I guess, in the solvable cases.
Fewer, but more importantly,
bound.
of bounded complexity in
Yes.
some sense or other.
Mm. Mihai, you have.
Yeah, so for this method, you need to generate the sequence of numbers, right?
Yes.
And for some problems, the sequence is more easily generated than for others, right?
Yes.
So, for instance, for this prudent walk or quasi-prudent walk, it's significantly easier to generate than for the full self-avoiding walk.
Yep.
Is that right?
Yes.
So then, there's also this fight to get the contributions as close as possible to the the lambdas and the mu's as close as
Yep,
possible
yep,
to
yep.
the self-avoiding walk. So then you have to keep somehow two competing things in your mind. You want the thing to be easy to generate, and you want to bring the lambda out.
Yeah, and you want it to be as close as possible to the problems you can't solve.
That's right.
Yeah.
So then, I guess there's a lot to say about a model which can be easily generated or something, right? So it seems that a significant difficulty is to come up with a better approximation of the self-voiding walk. Is that right?
Yeah. That you can solve, ideally.
You can solve-
Yeah.
or, and also there's this question of being actually solvable or being generatable, right?
Mhm.
So they are related, or
Well, it almost depends on which area of mathematics you talk to. If you talk to people who work in algebraic combinatorics, they will say that if you have a polynomial time algorithm, that's a solution. And certainly computer scientists would agree with that. Well, depending. If you talk to a mathematician, I think they would find that unsatisfactory. But it's almost a question of philosophy, isn't it? Right?
May I also, when I was talking about the catalytic variable, which is maybe giving you a true definite function, for example, at a value 1 over x instead of the appropriate value 1,
Yeah.
and maybe the true value x is the one you are interested to near the singularity larger than 1, for example. This would also give you a bound on lambda, because you are 10 by 10, you are having positive powers of your catalytic variable, which is evaluated at a smaller number. So if you can exactly solve a totally non-physical model, because there is a catalytic variable which is taking its non-natural value, this is maybe giving you a bound which is better than other bounds, in principle. Which is not in terms of a restricted family, but of the whole family with fancy coefficients.
I mean, I think most of the advances that we have in these problems, and speaking quite generally now, come from embedding a problem that you can't solve into a bigger space. And that's really that's an example of that. I mean, here we said...
Which advances? The negative advances?
No, let's get grandiose. Fermat's last theorem, Wiles didn't just prove Fermat's last theorem, he proved a much larger result in which Fermat's last theorem was a consequence. Perelman's work on the Poincaré conjecture wasn't a proof of the Poincaré conjecture as such. He generalized the problem and proved something much more general. And I think along the same philosophy, what Andrea is suggesting is embedding this problem into a. I mean, I'm not comparing but we're generalizing the problem, embedding it into a larger space, and maybe you can say something about the problem that you're particularly interested in. That's a good idea. I'm not sure what catalytic variable you would choose and how you would do it, but.
So that's basically the philosophy of catalytic variables.
Yeah.
Right? Enlarge the problem with more parameters counting more things so that you get closed form functional equations?
Well, it's not based on that philosophy. It's just that if you try and count these guys, this catalytic variable arises naturally. We don't know how to count it without the catalytic variable. It's not that we do it, we want to do it, we'd rather not.
It's okay.
Thank you.